Suppose I wanted to move one of these disks. How could I do it? And obviously that's one way of doing it. But there is another way. I've got them on a piece of stretchy rubber. So the second way of doing it is simply to stretch the rubber. And it's the movement of the rubber itself which carries the disk along with it. Now, this, in fact, is a very good analogy for the expansion of the universe. These galaxies here are not so much moving through space as being carried along by an expanding space. In fact, galaxies take part in both kinds of motion. If you're thinking about how the galaxy moves within its local group or cluster, moving around the other galaxies, then that is motion through space, the normal kind of motion. But if you're thinking about a couple of clusters of galaxies and why they are separating due to the Hubble expansion, then that movement is due to the expansion of the space between them. If you're thinking about a very distant galaxy or cluster of galaxies, then that kind of motion due to the expansion of space becomes the dominant motion. Now, it's very important to get the distinction clear between those two types of motion, because this sort of motion, where you're thinking about motion through space, that is governed by Einstein's special theory of relativity. As you've probably heard, one of the requirements of that is that nothing can travel faster than the speed of light. But if you're thinking about the other kind of motion due to the expansion of space, then special relativity has nothing at all to say about that. And therefore, there's no reason why speed should not exceed the speed of light. In fact, if you're thinking about a galaxy which is so far away it's beyond the horizon of the observable universe, then sure enough, they can indeed be moving faster than the speed of light. Right, now, this is actually quite a good analogy in as much as not all distances here expand. As I stretch the rubber, the disks themselves obviously don't change in size. And that is also the case with the galaxies. Although the space is expanding, the galaxies themselves do not change in size. And that's because they, like the disk, are a bound system. In that case, what you've got is gravitational forces holding the stars together, and that not only holds the galaxy together, but it keeps it the same size. So it's only the distances between galaxies that change. Actually, of course, it's pretty obvious that you can't have all distances changing, otherwise you wouldn't actually know that anything had happened. If you have a distance which it doubles in size, but I measure that with a ruler which also doubles in size, you get the same answer. So you can't have all distances changing. There's one way in which this is not a good analogy, and that is, of course, that the rubber sheet has got edges to it. And as far as we know, three-dimensional space does not have an edge or a boundary to it. It just carries on. Also, this sheet has got a central point, which I think would be somewhere like there. Now, why do I say that? Well, I'm judging it as being equidistant between the two edges. But as I say, with three-dimensional space, if there's no edge, then I've got no place from which to judge where the center might be, the center of the universe. So any point in space is as good or as bad as any other. Right, well, whilst we're thinking about this expanding space, how about another problem which might be bothering you, and that is the cosmological redshift. Now, what actually is the origin of that redshift? Take this lamp. It's blue, at least it looks blue from here, from close up, but what would it look like from a long distance away? Now, suppose we were looking at it from a distant galaxy across space. Well, let's go and find out, shall we? Well, from over here, it looks as though the light is red. Yet the strange thing is, for someone who is actually still over there by the light source, it would still seem to be blue. So, the colors are different. And that means, of course, that the wavelengths will also be different. It's shorter at emission than when we receive it. And how does that come about? Well, whilst the wave is traveling towards us from the distant galaxy, the space between us and that galaxy expands. These humps aren't bound to each other, so the distance between them well, they will also expand. And the further it has to travel, the more it will expand. So although the light has its normal wavelength at emission, it is redshifted by the time we see it. The lengthening of the wavelength occurs during the journey, and not at emission, which is what would happen if we had a normal Doppler shift. With the normal Doppler shift, due to the speed of recession of the source, all the lengthening occurs right at emission. And what we pick up is just simply that wavelength which was stretched out at the very beginning. Here what's happening is that the lengthening occurs during the journey. And the bigger the distance the light has to travel, the greater will be that lengthening. And that's very useful because it means that if we know what the wavelength was at the beginning, and we do know that from the atomic levels and the chemistry of the source, then from the redshift we can work out what the distance to the source is going to be through Hubble's law. The only trouble is that we don't know Hubble's constant particularly well, but, well, we're getting there. What is geometry? The geometry that describes the universe and everything in it. Well, it sounds a silly sort of question. You know, what else could it be other than straightforward, common sense Euclidean geometry? For example, if you have two parallel straight lines and you continue them on to infinity, then they would always stay the same distance apart. As for triangles, well, the sum of the angles of the triangle all add up to 180 degrees. And it doesn't matter what the shape of the triangle is or its size, you always get 180. As for circles, well, the circumference of the circle is 2 pi times the radius r. And again, it doesn't matter what the size of the circle is, you will always get 2 pi r. So that's Euclidean geometry. But there are situations where that kind of geometry doesn't work. And suppose, for example, you're trying to circumnavigate the globe. There you're confined to a curved surface, and Euclidean geometry doesn't work there. If we're to set up a geometry for this kind of surface, then obviously we need straight lines to start with, and obviously to some extent there isn't a straight line there, they're all curved. But if we choose as our definition of a straight line that it's the shortest distance between 2 points, and suppose we have 2 points, one there and another up there, then clearly there must be one line there which will be the shortest distance between those 2 points, and in fact it's this line here. It's a line of longitude. And in general what we find is that between any 2 points the shortest distance, the straight line, is the arc of a great circle. A great circle being one that lies in a plane that passes through the center of the sphere. So all these lines of longitude are technically straight lines, and so also is the equator. So we've got our straight lines then. How about parallel straight lines? Well, yes, we can take any pair of lines of longitude, let's take that one and that one, as they cross the equator, because we know that that angle there is 90 degrees, and so is that one there. So these two lines are parallel. So let's now extend those to infinity, or at least as far as we can get on this surface. And obviously what happens is that those two lines, they don't stay the same distance apart as they did before, they actually converge and intersect there at the pole. So that's the first big difference between geometry on a sphere and geometry that is flat. How about the triangle? Well, I've drawn a triangle on here. We need 3 straight lines, so I've chosen 2 lines of longitude, this one and that one, and for the third side I've chosen the equator. Right, now looking at the angles of that triangle, clearly this is 90 degrees, we've said that before, and so is that, so add those two together and that gives us 180. But you know, we've still got to add in that angle there, so whatever that might be, it's obviously going to end up more than 180 degrees, the sum of the angles of that triangle. In fact, that is true not only of this triangle, but of any triangle that we draw there. It always comes out to be more than 180 degrees. All right, if you have a very tiny triangle, an absolute sort of tinsy-wincy little triangle such that it covers an area which is more or less flat, then the sum will come out to be roughly 180 degrees. But it will still, strictly speaking, be a little bit more. Right, thirdly, what about a circle? Well, let me draw a circle on here, and to make things simple, let's me just draw it to be the same radius as we had here. So we'll take the pole as being the center of the circle, and I swing this round, and lo and behold, the circle happens to be the equator, right? So the equator is the circle of radius r that we had before. So now let's just compare the circumference of the flat circle of radius r with the one on this surface. Well, as you see, there's no comparison at all. The circumference of the equator is obviously much smaller than we've got here. And of course it has to be when you come to think about it, because this radius is curved. And that's what one finds with all circles that we draw on this surface, that the circumference comes out to be less than 2 pi r, because remember, this is what is 2 pi r. So that is what we call spherical geometry. And as you see, it's very different from flat Euclidean geometry. But even that doesn't exhaust the possibilities. Now, suppose, for example, we had a surface like this, the kind that a horse flea perhaps would have to learn how to negotiate. A saddle shape, or as we sometimes call it, a hyperbolic shape. Well, again, the first thing we have to do is to identify straight lines. And again, we use the convention that it's the shortest distance between 2 points, so that gives us some straight lines. How about parallel straight lines? Well, there are a couple down here. That one and that one. They are parallel. And if we follow that through, well, you see that, again, they don't stay the same distance, and neither do they intersect with each other as they did on the sphere. They diverge. So that's a big difference from the sphere. Triangles, yes, I've got a triangle over there, and as you can probably judge without measuring it, that the sum of the angles of that triangle are going to turn out to be less than 180 degrees. All right, now you might think I'm cheating a bit, because you might think, well, he's actually only got one decent straight line there. The other two are curved, and he's deliberately curved them in order to make the sum come out less than 180 degrees. But actually, that's just a trick of the perspective. If I swing things round a bit, you'll find that straight line begins to look curved, and the line on the left now begins to be the one that looks like a straight line. So what I'm saying is that you must be very careful not to go by appearances and stick by the convention that these lines are the shortest distance between 2 points. And so, okay, with that triangle and any other triangle that I draw on here, the sum comes out to be less than 180 degrees, whereas on the sphere it was more than 180. Finally, how about a circle? Well, let me again draw a circle on our curved surface with the same radius as we had originally, and we'll take the point here in the middle as being our central point, and well, as you see, I've already drawn that circle in there. This is the circle. And so what I have to do now is compare that new circle with our flat one. If I just clip that in there, I think you'll agree that's a pretty good fit, that side. So let's swing the whole thing around and see how it fits on the other side. As you see, it doesn't. There really is a big difference there. And again, I'm not cheating. If I take our radius, you'll see that it really is a circle of radius r again. And as you see, it turns out this time to be very much larger than the circumference of the flat circle. So what this means is that on this surface, the circumference of a circle is greater than 2 pi r, whereas there it was less. Right, now you may be saying, well, why bother with all these different kinds of geometry? Well, the point is this, that it could well be that Euclidean geometry does not apply to the universe. Now, I glibly started off by saying that these two lines, if stretched to infinity, would remain the same distance. But how do we know that? We've never actually ever stretched lines to infinity. As far as we know, if we actually did the experiment, we might find that they intersected like they did on the sphere, or diverged as they did on that hyperbolic surface. As for triangles, well, yes, if I measured these angles, I'd find that they come to 180 degrees, as precisely as I can measure it. But this is a small triangle, you know, compared to the size of the universe. And we saw on the sphere that if you had a very tiny triangle, then even there you would get roughly 180 degrees. What would happen if we had a huge, an absolutely gigantic triangle? No, suppose, for example, that's us on our galaxy, and we had another observer on a different galaxy, and yet a third one over there on another galaxy. And suppose each of us took lines of sight to the other two galaxies and then measured the angle between the two. And then somehow we pooled our results and added the three angles together. What would we get? Would it be 180, or would it be something somewhat larger, as we got on the sphere, or smaller, as on the saddle? We don't know. We haven't done it. And as for the circle, okay, it's roughly, as close as one can say, 2 pi r. But again, if we had an absolutely huge circle, what would we get then? We don't know. In fact, we do not know what the geometry of the universe is. It's one of the big problems of cosmology. Well, fortunately, we don't have to go out there and measure these huge triangles and circles. We can adopt a different tack. Instead, we can go for that feature of the universe which determines what the geometry shall be. And that's the density of matter and energy. Now, when we look at the matter that we can see and we add up the amount of it, the luminous matter tied up in the stars, it actually doesn't come to very much. The average density based on that is very small. It's a very dilute universe. And on that basis alone, one would assume that the geometry would be hyperbolic. But we have to be careful. As you know from chapter 2, luminous matter is not the whole story. There is also dark matter there. We can't see it directly, but there are indications of it, and those indications show that there's a lot of it. In fact, more of it than the luminous matter. And who knows? It could be that there's so much dark matter there that it actually tips the scale over so that the geometry becomes one of those other two. We simply do not know what the geometry is. But there's one thing we do know, and that is that this universe is expanding. And so whatever the geometry will be, it'll be an expanding geometry. Either spherical expanding geometry, or it could be flat expanding geometry, or it could be hyperbolic expanding geometry.
All through this course, we've seen examples of the way modern telescopes have opened our eyes to new phenomena. The outstanding advances have been in detectors, and we'll look at some of those in a moment. But astronomers don't just put a suitable detector at the focus of a telescope. There are vital and often quite complicated optical elements for the incoming radiation to pass through before reaching the detectors. No two instruments are the same, but there are some common elements. The first component might be bandpass filters to choose the particular wavelength region for which the detectors have been designed. Then there will be a lens to give the beam the degree of convergence, what's called the F ratio, suited to the input aperture of a spectral analyzer. Then inside the analyzer itself, which may be a simple diffraction grating, but more often is a combination of a coarse grating, called an A-shell, and a fine grating. This combination spreads the spectrum out into a series of bands to give high spectral resolution and broad coverage. There will also be several mirrors to switch the beam between different lines of optics, leading to different detectors. One of these will be to a camera to provide an image. Some sort of image will always be needed to locate the source. Not usually as obvious as the sun, of course, often just a faint star or a distant galaxy. Sometimes the astronomer's work will be based on an image, which must then be of the highest quality possible. But for every image, there will be many spectra to be recorded to work out the chemistry and dynamics of the source. This optical instrument maximizes efficiency because the spectra for an array of points in the image are recorded at the same time as the image itself. The same thing is done in radio wavelengths. Here are some results displayed as images at different wavelengths, but they could also be displayed as spectra at different points. So big, expensive telescopes use very sophisticated, powerful detectors. In the case of telescopes for spacecraft, they must be assembled in huge clean rooms like this one, where one entire wall is made of air filters.
This is the largest clean room at Goddard Space Flight Center. We use it for processing payloads for the space shuttle, especially scientific instruments to go onto orbiting satellites, sometimes whole satellites. We take the equipment, we test it in here, we assemble into larger modules and basically get it ready for a launch into space. And in those scientific instruments, the most important components are the detectors that receive the radiation. An incoming photon of light strikes the detector surface, releases electrons that travel on inside the detector, and we detect them and count them and measure the radiation by that means. All across the electromagnetic spectrum nowadays, these detectors are approaching their theoretical sensitivity limits. They're getting about as good as they can get in most cases, and they're different in every energy range. The infrared, for example, we use the two-dimensional arrays so we can make an infrared picture that are made of such materials as indium antimonide or mercury cadmium telluride. And by selecting different materials for your detectors, you can detect different ranges of the infrared wavelengths. In the optical or visible light, we're using primarily the charge-coupled devices. These are, again, two-dimensional arrays. They're extremely sensitive, and you use one of these arrays nowadays with, say, a 1-meter diameter telescope, and you can take a picture that's as sensitive, you can see as far out as you could 10 years ago with a 4-meter telescope, just using photographic film, the way we used to take these pictures. In ultraviolet light, we've used such detectors as the digicons on the Hubble Space Telescope. And in these, an image of the spectrum, the incoming light, is focused on a photocathode, and it produces an image of the spectrum in electrons that are magnetically focused within the tube. And they fall on an array of diodes. And each diode counts electrons corresponding to a different wavelength in the spectrum. We call it an electron image of the spectrum. You detect the ultraviolet light in that manner. There are two-dimensional detectors now for ultraviolet light, in which you can make an observation, for example, in which you have one dimension in the detector that's a spatial dimension on the sky, and one dimension on the detector that's the spectrum. The wavelength varies along that dimension. And you can make an observation in which the spatial dimension is the radius coming out from the center of a galaxy. And so in one exposure, you can simultaneously record the ultraviolet spectrum at each point along that radius. And we call this a multiplex advantage. In one observation, we can get many spectra that previously we would have had to move the telescope to take a spectrum at each separate location.
We want to do this in space because we want to look in the ultraviolet in order to look at all of the absorbing lines which naturally occur in the ultraviolet. These can be shifted at very large distances into the visible, so some of this work is done from the ground, but we have a gap in our knowledge. If we look only from the ground, we can only see what happens very far back in time, and we can't connect it to what's happening now. In order to connect it to what's happening, say, in the last 5 billion years or so, then we need to look in the ultraviolet, and that's what we'll be doing. For this, we need detectors which are specific to the ultraviolet, which are not sensitive to the visible and are only sensitive in the ultraviolet. Such a detector you can see here. This is a microchannel plate, and we coat this with a cathode which is only ultraviolet sensitive. This particular detector has 1,000 elements in one direction and 1,000 elements in the other direction, so you get 1 million picture elements overall. If you look in a microscope, then you will see that this is composed of millions of tiny tubes. Each of these tubes takes in an ultraviolet photon and converts it into an electrons and amplifies it so that you get about 1 million electrons out of the back. Then in a particular device which was invented by Dr. Gethin Timothy of Stanford University called the multi-anode microchannel array, in which each electron cloud is picked up by the electrodes and converted electronically into a signal which identifies the position on the array. This is called a photon counting detector. So we will use ultraviolet observations from space with visible observations from the ground in order to put together the whole history of the chemical evolution of the universe in time.
In the X-rays, you have the advantage for making images now of the nested grazing incidence mirrors. The X-rays glance off one of these mirrors. You can focus them and make an image in X-rays that goes into a gas-filled imaging proportional counter like are used on the ROSAT X-ray satellite, and then the X-ray photons in that image cause electron events in the chamber which you can count, and you know at what position each event occurred, and you build up a picture of the sky in X-rays. The gamma rays, there are different kinds of detectors for each broad range of gamma ray energies. On the Gamma Ray Observatory, we've used spark chambers for the energy range from the tens to the hundreds of millions of electron volts. That's the energy of each individual gamma ray photon. What happens is photon comes in, it passes through a thin metal foil, produces an electron-positron pair that move on to the spark chamber, which is gas-filled cavity between two of such foils, and it causes an electrical discharge that we can count, and that's how we detect the gamma rays. Some of the gamma rays pass right through, and they go to another foil, or another, before they actually create a pair. And so you have a series of foils and spark chambers in such an instrument. And that's how we record even the gamma rays, which was almost unthinkable not many years ago.